Here's the question that I ended the previous part of this lecture with, and note that I've given you all the information you need in the graph. This light green line that directly connects the point at t4 to the point at t9 is what we would use to get an average y component of the velocity. We just take the slope of this line. That's the straight rise over run from this point to this point. On the other hand, this tangent line to y at t4 is what we would interpret as the instantaneous velocity at t4. And we can see that the light green line is steeper than the dark green line, and so the average velocity is larger.
A lot of you are probably feeling pretty intimidated right now. I just introduced a whole lot of math that you have never seen before. This is calculus, and after all, most of you are just starting to take your first calculus course right now. You haven't learned about derivatives, so how the heck do I expect you to understand this? Well, all I need you to understand is a few things about the meaning of the derivative for now. Derivative means slope. More specifically, it means the slope of the tangent line to the function. And so we are imagining that we can model our data with a function, y of t, and that we know how to extract from that function the slope of its tangent line at any t. That new function that gives us the slope is called the derivative. You'll learn how to take the derivative in calculus. For now, all you need to know in physics is that when I write that derivative, dy by dt, it just means the slope of a tangent line to the y versus t graph. Notice that we can't really get instantaneous velocities from our data. All we can do is get average velocities over time intervals and make those time intervals small enough that those are going to be reasonable approximations to instantaneous velocities. Well, let's see how we do that. So here's our falling ball data, and I've set up a graph so that we'll see the Vy versus t as soon as I've generated it, and I'm going to generate it in this column here. But I'll warn you before I start out, I'm going to deliberately make a mistake that I often see students make. So here we go. I know I need to take a displacement over a time, right? So here, I'm going to take this displacement between here and here and here. And now I'm going to divide by the time, right? Okay. And now I'm going to apply that to all these other points, and voila. Okay, there's our Vy versus t, but look at that. Does that make sense? It seems to be saying, other than this odd point here, that Vy is about 0.3 meters per second, more or less the whole time the ball is falling. But that doesn't make sense at all. We know from the y versus t data and the fact that it's getting steeper that the ball must be speeding up. So this is nonsense. What have I done? Well, maybe you saw. I took a displacement and I divided it by a time. Should I be dividing by a time? Remember, the times depend on when you defined t equals 0. We should be working in time intervals, which don't depend on when I set t equals 0. So let me do that. I'll change that to the time interval that is this time minus this time. And now I'll apply that down the whole thing. And there is our Vy versus t data. And look, Vy is increasing as we expect, and what's more, it looks like it's roughly a straight line. Let me just remind you how to interpret this y component of v versus t graph. At each moment, we're thinking of finding a slope of a tangent line to our y versus t graph. Now, we're not quite finding the slope of a tangent line, we're approximating it by an average velocity calculated over a small interval. But in any case, once we have the value of that slope, we then plot it as the value of Vy at that time. Now we move on to a different time and find the slope there, and we plot that as the Vy at that time. And that gives us our whole Vy versus t graph. Now, we can think of this as being our measurement of the instantaneous velocity as a function of time. It's an approximation because we were getting it from average velocities, not actual tangent lines. If we now draw a best fit line through our data, that's an approximation to the function Vy of t, where what I mean by Vy of t is the thing we would have got if we knew the function y of t and took its derivative. I want to mention one more thing we can do with our velocity versus time graphs, and it's going to preview another little bit of calculus that we'll eventually see. Let's think about this object in this velocity versus time graph. You can see from the Vx versus t graph that this has a constant x component of velocity. How far in the x direction does this object go between t equals 1 seconds and t equals 4 seconds? Well, you know that the Vx is from the displacement over the time, and you can just rearrange that to solve for the displacement. And so that shows you how to get the displacement. And so, look at how we can interpret that on the graph. The Vx is this height on the graph, and the delta t is this width on the graph, and we're multiplying them together. So in fact, what we're finding is this area under the Vx versus t line on the graph. Well, that works here. It turns out, for reasons that we'll see eventually and have to do with calculus, that this always works, even when the velocity isn't constant. So here's our falling ball data, and if we wanted to know what the displacement, the y component of displacement was of this ball between 0.2 seconds and 0.5 seconds, all we would need to do is find the area of that shape underneath Vy versus t.